In this video, I'm going to talk about the chi-square analysis. This is an ideal analysis for testing relations between two categorical variables. And ideally, the categorical variables will have few categories. Most ideally, each one will have two categories. So for instance, if I compare whether or not one uses a wood stove and contracts sarcoidosis, a form of cancer, using a wood stove would be yes or no, and sarcoidosis would be yes or no. So each of those variables has two levels. 2 times 2 is 4. We get a table that has 4 cells in it for the 4 possible combinations, right? You can have yes, you can have wood stove, yes sarcoidosis, yes wood stove, no sarcoidosis, etc. So there's 4 different choices there. That's what we call a cross-tabulation table. I'll show you a picture of that in a second. The chi-square test compares the observed cell counts for those 4 cells to the expected distribution if individuals were randomly dropped into the 4 cells, right? So that's basically what it does. I'll show you how to calculate this equation here. The chi, it's not chai like the Oprah chai latte, it's chi as in sigma chi, if any of you are frat people. Chi is a Greek letter, so this is chi squared. Chi squared, and the equation is here. It's the sum of this ratio here. We have the O sub I. It's not oi, it's O sub I minus E sub I. So it's the observed value for each cell, where each cell, there are let's say there's n different cells in each cell, and we'll let I equal a cell. So if there's 4 cells, I can go from 1 through 4. So it's the observed value for that cell minus the expected value of that cell squared divided by the expected value of that cell. We have to calculate the expectation. The expectation is calculated by the column total, and I'll show you what that means in a moment, times the row total divided by the total. It's an interesting equation. It comes from what we call a binomial distribution, where the expected value of the binomial is n, which is the total sample size, divided by the probability of being in that cell, and it just works out to be this. That's beyond the scope of this course. I'm not going to really show you an example of how that's derived, but you could if you want to. So here's a question: does the use of a coal stove result in sarcoidosis? This is our cross-tabulation table. We look at the rows. The rows indicate whether or not one has sarcoidosis, yes or no. So 17 individuals do, and 113 do not, out of a total of 130. We're using probability language here, so we say success and failure. So in this case, there are 17 successes and 113 failures, although obviously having disease not qualitatively a success, but in probability terms, that's what we're looking for. Or excuse me, that's 17 people use a coal stove and 113 do not. In terms of sarcoidosis, which is the columns, we have 45 individuals have sarcoidosis and 85 do not, so there's 45 successes and 85 failures. In carrying out any statistical test, we first start by writing out our hypotheses. We have a null and an alternative hypothesis. The null hypothesis is the one we'd like to reject in favor of the alternative hypothesis. And we write out this null as using a coal stove is not associated with sarcoidosis. And the alternative is the one that's labeled H sub 1. Sometimes you'll see H sub A. It's using a coal stove is associated with sarcoidosis. Our alpha levels are probability of a false positive result, which we select in this case to be 0.05. That means we'll select a 5% chance of being wrong, or at least being wrong in that we have a type 1 error, false positive result. To find, well, we have to find a critical value, since we're doing this by hand, and what one would do here, and we're not using a critical value table, we're only dealing with a 2 by 2 distribution or 2x2 cross tabulation table, the chi-square critical value for a 2x2, well, the critical value depends on the degrees of freedom and the alpha. The degrees of freedom are the rows minus 1 times the columns minus 1. So we have 2 rows and 2 columns. You'll see it's 2 minus 1 times 2 minus 1 equals 1. And this is what you'll always have when you have a 2x2 table. And the chi-square critical value in that case is 3.84. It's always 3.84 with that alpha. So what is a critical value, by the way? To be statistically significant, our chi-square value has to be greater than that value, greater than or equal to that value. So that's what we're looking for. So we need this critical value. If you're doing this by computer, you would rely on a p-value, and you want your probability to be less than or equal to whatever your alpha is. In this case, it's 0.05. But we're doing this by hand, so we'll use the critical value instead. We'll go ahead and calculate the expected value. Well, there's 4 expected values. There's 1 for each cell. So we'll label these. I don't know if I wrote this. No, I didn't do it again. So let me show you. We'll label each of these cells. This is cell 1, 1, since it's row 1 and column 1. We'll call it cell 1, 1. This is cell 1, 2, the one with the 5 in it, since it's row 1, column 2. And then down here for the no, we have row 2, column 1, and they meet at 33. So this is cell 2, 1, and then finally this is cell 2, 2, since it's the nexus of the no's. So we have row 2, column 2, so that will be the cell that includes 80. Our total is 130. So for the expected value of this first cell, it's the row total, which is 17, right? You see the total here, times the column total, which is 45, divided by 130. That's our total, and that's what we get. 17 times 45 divided by 130, that equals 5.885. Let's do another one. Let's look at cell E12, or the expected value of cell 1, 2. That's row 1, column 2, so that's the one that has 5 in it. So we have the same row total, 17, but now the column total is 85. So we have 17 times 85 divided by 130. And we get 11.15. We do the same for the next 2 cells. That's on the second row. We have 39.115 and 73.885. The next step is to carry out the equation. So it says sum, so the sigma means sum, right? Sum these ratios here. So we have 12. So the first cell, cell 1, 1, has an observed cell value or cell count of 12. So there's 12 successes. Again, we use a success failure terminology. If you're a member of this cell, that's a success. If you're not, it's a failure. So we look at the observed number of successes minus the expected number of successes, right, for that cell. So it's 12 minus the 5.885 squared divided by 5.885. And we do the same for cell. So this is for cell 1, 1, cell 1, 2, cell 2, 1, cell 2, 2, because we're summing across the 4 different cells. We carry out that summation and we get 11.180, and that's our chi-square value. So what we do then is finally we compare it to our critical value, and you should always write down the rejection rule. I should have written it down here. Well, here I can. Actually, I can. To the critical value. Here, I'm going to write this down, and in my stats class, I teach everybody to write down the rejection rule. Down the rejection rule, or decision. I call it decision rule. Decision rule. Oops. Let's say reject the null hypothesis if the calculated value is greater than or equal to the critical value. So that's what we want to do, and we look at our calculated value, and it's 11.80. which is greater than our critical value, which is 3.84. So we would reject the null hypothesis that there is no relation between a coal stove and sarcoidosis. So there is a relation then. Now, we want to provide an effect size, and we already know how to do this. We know how to calculate an odds ratio, but let's do it again here. So we want to know what's the odds ratio then for sarcoidosis among those who have a coal stove versus those who do not have a coal stove. And that is going to be, so let's take a look at this again. So it's the ratio of the odds. The odds are success over failure. So we have 12 successes. Again, we're using the success not qualitatively, but just in terms of stats. It's 12 of the 17, so it's 12 divided by 5 in the numerator, and then 33 divided by 80 in the denominator. But we also know that one thing we know is that when we do an odds ratio, we do a cross product. So 12 times 80 divided by 5 times 33, and that's what we have here, right? 12 times 80 divided by 5 times 33, so we get 5.818. So this tells us that, I'm going to jump ahead to the interpretation. That tells us that individuals who have a coal stove or a wood burning stove are almost 6 times more likely to have sarcoidosis than those who do not. And then, of course, you can calculate a confidence interval. I say optional because in this course, you don't have to do that, and usually I do it as extra credit. There'll be a couple of extra credit opportunities on this final. If you recall that in order to calculate the odds ratio, we have to take the odds and put it in a natural log scale because we want this to be normal, as the odds ratio is not normal, and we want to use the beauty of the normal distribution. We know that 95% of all values are between plus or minus 2, or it's 1.96, which is 2 standard deviations of the mean. So we calculate the confidence interval. It's 1.96. This is the margin of error, 1.96 times the standard error, and this square root of all the reciprocals of each of the cell counts is your standard error. I'm not going to go into detail here because I already did that. So we end up making this calculation here, and then we exponentiate the results. So I generally break it down into the exponents, right, like this, and then do the exponentiation to finally get the 95% confidence interval in this case. So what we get here is that the odds of sarcoidosis among those who are exposed to this wood burning stove are nearly 6 times greater for those who than among those who do not have a wood burning stove, and the 95% confidence interval is 1.899 to 17.819 because this value does not cross 1. So this doesn't include 1, but I mean both of these values are above 1, and 1 means that there's no relation because an odds ratio is a ratio of odds. If it was 1, that means the numerator and the denominator would be equal. So since this doesn't include 1, we know that we have a significant relation, which it verifies what we found with our chi-square test. Okay, well, thank you very much. I hope this was helpful, and we'll do some more practice later. Bye.